Okay, so here we are again with a recording, which you are listening to if you're home on a snow day, so enjoy that. First of all, notice the extra credit assignment at the top. Second of all, you may want to try the bell ringer quiz from yesterday's notes and make sure that you understood that. These are our target skills for today that hopefully you will have learned at the end of the lesson. We do now have Math Excel up and running. So you'll want to go to the whsmontgomery.weebly.com website and open the instructions for Math Excel sign up. Follow the instructions to set up an account, and I will get notification when you have enrolled in the class. You can do homework for section 2.3, one of two choices. If you're able to get into Math Excel successfully, you can do that, or you can do the book assignment, either one. Section 2.3 is about polynomial functions and their graphs. You can go ahead and read over this. Pause when you are finished. You can go ahead and hit play again. All right, so this section is about polynomial functions. So that would be functions of second degree or higher, so second degree, third degree, fourth degree. You can look over here some examples of what is a polynomial and what is not a polynomial. Again, pause this as you need to review it. Polynomial functions are smooth and continuous graphs, as you can see right here. They have no breaks and no points. Not polynomials. These graphs are broken, so this has what we call a discontinuity. It's discontinuous, or it has sharp points or turns. So these are not polynomials. Next, we want to talk about the end behavior of polynomial function graphs. So if you have a graph where the polynomial power, highest power, the degree is odd. So we're here where the degree is odd, that's the n is odd, both of these cases means the highest power on x is odd. Then the graph has end behavior where it's one side is down, one end is up. So here one end is up, one end is down. Which of these is depends on the leading coefficient. So here this leading coefficient is a sub n. When the leading coefficient is positive, this is the way the graph looks. So for example, y equals x cubed has a positive leading coefficient of 1, so it falls to the left and rises to the right. If you have a polynomial function of odd degree where the leading coefficient is negative, then this rises to the left and falls to the right, exactly opposite of this one. For even powers, so n is even here, this is to the fourth power. For all even powers, both ends rise or both ends fall. And which of these it is depends on the leading coefficient. So these are even powers, leading coefficient positive, both ends up. Leading coefficient negative, both ends down. If we look at this example, you can use the leading coefficient test to determine the end behavior of the graph. Notice that the degree is odd and the leading coefficient is positive. So this graph looks like this. Okay, so that's left end down, right end up. Go ahead and try checkpoint 1 on your own. Pause. Okay, and the fourth degree polynomial has either both ends up or both ends going down. And we look back here to see it's a positive leading coefficient, so both ends up. Left end up, right end rising as well. Let's go on to zeros of polynomial functions. Remember that we have zeros, roots, x-intercepts, and solutions, all the same thing. Finding the zeros of the polynomial function. You want to go ahead and write down this example with me. Right now, the only method that we have for solving third degree or higher polynomials is factoring. So we're going to do factor by grouping with this one. Remember, in factor by grouping, you group two terms that you can factor something out of, and then other two terms that you can factor something out of. I've chosen to split them this way. From the first two terms, I factor out an x squared, leaving x plus 3. From the second two terms, I factor out -1, leaving x plus 3. The next step here is going to be looking at the two terms. There's one, there's the second term. And from these terms, we can factor out an x plus 3. So there's an x plus 3 here and here. Factor that out, which leaves x squared plus -1 or -1 here. Now we're ready. We have this factored. We're ready to set the factors equal to 0. This one actually will factor a little bit further, which you'll see down below. But I set the x plus 3 equal to 0 and set the x squared minus 1 equal to 0. Remember, we set factors equal to 0 to find roots. So factoring this one further, we get x minus 1 equals 0 and x plus 1 equals 0, yielding the roots -3, 1, and -1. Go ahead and take a minute to try this one on your own. You'll notice there's a different type of factoring required for this one. We're going to do GCF factoring. The greatest common factor for each term is the -x squared. Factor that out, distributive property, which leaves x squared minus 4x plus 4. This trinomial can be factored further into x minus 2, x minus 2. Remember, you can pause this anytime you need to write down and catch up. X squared equals 0, or -x squared equals 0. You take the square root, you get x equals plus or minus 0, which is just x equals 0. We get that twice. Both of these factors also yield an x equals 2. Technically, there are 4 roots here. This was a 4th degree polynomial, but there are really only 2 unique roots. We would say that these roots have multiplicity of 2 or even multiplicity. So this also has a multiplicity of 2 or even multiplicity. I will sometimes call this a double root, and this is a double root. If we look at example 7, we have an already factored function. It says to give the multiplicity of each 0. So what you would want to do is set the factors equal to 0. All right, and each of the factors here, not including the constant that's in front, this doesn't count as a factor unless it has a variable in it. So the factors are x plus 1, 2x minus 3, and another 2x minus 3 because of the squared. So we have, these are the 3 factors, set them equal to 0 and solve, and we get these 3 roots or zeros or solutions. Notice that x equals 3/2 has multiplicity 2, okay, or even multiplicity. That means that the parabola just, not the parabola, but the curve just touches the x-axis. It doesn't cross through it. And then at x equals -1 is an odd multiplicity, so it actually crosses through the x-axis here. Okay, notice the difference. Take a few minutes to read your steps to graphing a polynomial function. We have a leading coefficient test. We have finding x-intercepts. We have finding y-intercepts, considering the symmetry, and then the turning points, which also could be a vertex. I'll go through the steps to graph this one, and go ahead and pause when you need to, but do this one along with me. Okay, so per step 1, we need to consider the end behavior. So if you look here, we've got even degree and leading coefficient that's positive. So we would expect this to look like a W. Step 2 is going to be to find the x-intercepts. Remember, that's plug in y equals 0 and factor. I'll do that next. All right, here's my work for factoring. This is a 4th degree polynomial that actually kind of behaves like a quadratic trinomial. If we consider the FOIL backwards process, the first term splits into x squared and x squared. The last term splits into 1 and 1. And this means same sign, and we look back here, they're both negative. So I have x squared minus 1 and x squared minus 1. Each of those factor further here. Set each of those factors equal to 0 and solve. So altogether we have 4 roots, which are 2 distinct roots of 1 and -1. Okay, so each of these roots has multiplicity 2 or even multiplicity. that means that the curve will just be touching the x-axis, not crossing through it. It should look something like this. Okay, so we have the parts of the W here and here touching the x-axis. These are the x-intercepts. The next step, step 3, is to find the y-intercept by computing f of 0. So let's do that next. Okay, by plugging in 0 into the original function, f of 0, we get 0 minus 0 plus 1. So f of 0 equals 1, or the y-intercept is 1. That goes here. So now we know kind of where the top of the W is. Step 4 is use symmetry if applicable. Okay, in this case we are going to have symmetry. We can tell this because of the roots and because it is even about the y-axis. If we plug in f of negative x, the function would stay the same. That means it's even. Step 5 says use the fact that the maximum number of turning points of the graph is n minus 1, where n is the degree. So the degree is 4, so the maximum number of turning points is 3. And I think we can see that here. Let's draw in the W. There's one turning point, there's another turning point, and there's the third turning point. So that's a little bit wide, but I think you get the idea. Okay, that concludes the lesson. Go ahead and try the homework for this, and I will see you soon.